Welcome back to After Hours Engineering. In this episode, we return to building implementations and build the core component of our processor, the Arithmetic Logic Unit, the ALU. This is sometimes seen as the execution part of a processor because it performs calculations that influence the flow of data. In our design, we are going to combine both the arithmetic, the add and subtract, with the logical, the shift left and the shift right, into a single module. Now before we start building our module, let's take a look at a couple of different approaches to modeling within Verilog. We could build our ALU using the gate level modeling. On the left we have a very simple adder to stand in for the ALU. On the right is what the Verilog would look like. Notice the explicit use of gate level constructs such as AND, OR, exclusive OR. We could design the ALU at a slightly higher level using an approach called data flow. In this mode, data flow tends to blend Verilog's behavior syntax with Verilog's Boolean operators, as we're seeing here with the sum and the cout. We're using the caret, the ampersand, and the pipe or the OR symbol to represent the Boolean operators, and the equation itself is the behavioral syntax. Or we could design the ALU using a purely behavioral approach. In this case, the continuous assignment is concatenating the carry out and the sum, but on the right side you'll notice that there are no gate level statements or Boolean operators. This makes it a purely behavioral level approach. As we previously did with the register component, so too, by extension, will we build all of our components using the behavioral model, including the ALU. So how about we go ahead and build that ALU module? As before, I have already designed the ALU, and I'm going to drag it into our processor here. Moved it to the wrong place. There we go. So here is our ALU module. As in Verilog, all of our modules start off with the keyword module, and eventually they end up with the word end module. So if we come up here to the top, we have our usual default parameters, which is 16, and the number of flags. Our ALU has 4 of them, but we're only concerned with the last flag. We have our inputs and our outputs. We have some local variables for easily referencing a bit within our flags register, and we have the internal results and a carry flag. Our ALU takes an input for a function. This is a 4-bit number, and we look it up. Now here we see a define. Where is that at? Well, we've got a second file I'm going to drag in that's full of constants, and here they are. These are all the instructions that we covered during the ISA session, and there they all are. Here is the specific instructions for the ALU. So here it is, our add. Now, if you look at the core piece of each one of these instructions up here, you'll see we have a behavioral statement. You'll notice on the right side of this equation that we have no AND gates or gate primitives. Neither do we have the Boolean operations that Verilog has. This is all a pure behavioral style statement. So in this case, for an add, we're going to add our 2 operands, A and B, plus the incoming carry flag. And we'll concatenate that all together in this result on the right side. Same thing for the subtract, but in our case, we're going to take A plus the 2's complement form of B that performs the subtraction. Shift left is using the shift left operator, and B represents how many positions we're going to shift. And the same thing for shift right. It uses the shift right operator, and B defines how many positions we're going to shift to the right. Once that's all said and done, we calculate the flags into one bulk unit. Now, our processor only understands the Z flag. However, for completeness, I'm showing you how to do the other flags. For example, the overflow flag is looking at both the pre and the post state of the uppermost bit to determine whether the overflow occurred. The negative flag is simply looking at the most significant bit to see if a negative result happened. And of course, our carry flag is coming from the operations that we had done above. And then finally the 0 flag, and this is the one we care about the most. It's the only one we care about, and it is a comparison between the 0 value here and the results calculated from above. We take the results, we put it into our output, and we're done. This is our ALU module. It's not that complicated, only because it has 4 instructions, but that's it. With the module built, we are now ready for simulation. And as with the register, we're going to need a test bench and a makefile. So let me drag over our simulation. I already have all of the files set up. I have a makefile, which we'll take a look at first. And as you can see, it's almost identical to the register makefile, except that it takes an ALU module. On top of that, I've added another parameter here called test target, and it defaults to simulate add. That is where we pass it to Yosys. And I take whatever target is defined as, which defaults as simulate add, and pass that to the simulation. So let's take a look at our test bench, and you'll see how this flag relates to it. So here's our test bench, and as usual we define some timescales. I define the output, and I define a module, which again has the _TB just as a convention. We have some inputs and outputs defined, and we have this very unusual clock here defined. And you might ask, well, our ALU is asynchronous, so it doesn't need a clock. However, I'm going to use the clock as a way to control where I make my tests during the flow of the simulation. It's not required, but it does help kind of break the data up in very discrete chunks of time. Again, here is the device under test, our actual ALU, and we have all of our inputs and our outputs. We have an initial statement to set up the dump file and the variables, any other statements we want to see. And here's the meat of the simulation right here. This is the include statement that brings in our constants file. You remember that had our ALU defines in it. And then we have our always behavioral block, which contains our test for the macros simulate add and simulate subtract. That goes back to that makefile, and here they come in. So let's just take a look at one of these, and we'll take a look at the add operator. So come over here, we load that in, we scroll up to the top. You can see that I'm waiting on the edges of the clock, both the positive and the negative. So here I define some flags at the positive edge of the clock, and then wait for the negative edge of the clock. Don't really have to do this, but it does break up the data. And then I do my assertion here. Then I'd set up for another test where I'm adding 2 other values. I wait for the negative edge of the clock, make my assertion, and then make another assertion. 2 plus 2 should equal 4. Again, and then I check flags, and then I come down and I do another test of known values where I'm adding 2 and hopefully get an overflow flag. In this case, I'm testing for the carry flag being set because I've got a very large value here, and we're adding 4 to it, which should send it right over the edge. And we continue on with each one of these tests, including all of the more convoluted tests for 2's complement and negatives. And this goes on until we finally get to the end where we end this simulation. That's it. That's the add operation. So if we go back to our test bench, you can see it'll either choose between the add or the operate. That's it. That's our test bench. The subtraction is almost identical, except the values are checking for the subtraction of each one of the variables. That's it. It's just a non-comprehensive test, by the way. There's a lot more you could do to test out all of the flags, but most of them were only concerned with the 0 flag in this case. So that's our test bench. Okay, with the module and the test bench built, we are ready to simulate. So let's head on down to the console here and type in our make space sim command, but we're also going to add in our additional macro here, and we're going to set it to simulate add. We'll run it, and there you go. So you can see here on the wave diagram that we have 2 inputs, A and B, and our output, Y, and then any output flags, inputs, and then the function that we're trying to simulate, which is the add, the number 2. So let's look at the values on each positive clock to see how they fare. We know that on the first clock, we're going to add 0 plus 0. We expect the results to be 0, but we also expect the 0 flag to be set because the results is 0, and that's what we expect. Now here we are on the 2 plus 2. We expect 4, but the 0 flag is not set, which is what we expect because 4 is not equal to 0. On the next one, we're going to add the previous B value, which is a 2, to F. And we do expect a 1 because it rolls over to a 1. However, it also caused a carry, so a carry rolled over, and that's what we expect. In the next one, we purposefully set up an FFE0 and a 40, and we add those together, a carry is generated, which is what we expect. In the next one, we purposely add 1 to this, bumps this up to FFF0. We expect that. We also expect that the negative flag, that's what this bit here has gone high. And the reason is because one of the operands had the most significant bit set, which gives us a negative value. That's what we expect. Now let's look at another case where we're adding two numbers where only the most significant bits are set, which is 8000. When we add those together, we get 0, but everything rolled off the end here, and that gives us our 0 flag because it's 0, gives us a carry because of the rollover, and it also sets the overflow because these two values overflow. The overflow makes most sense to sign values. So let's look at the final one, 7FFF with itself. This is the value we expect. We don't expect an overflow, but we get one because some of these two numbers causes an overflow, but it also causes the upper bit to be set, which is the negative flag, and it's not 0, and neither was a carry. So this is the case where we're dealing with two signed numbers, and if we look at the overflow, we'll be interpreting our two operands as signed. So there you go. That's the add operation. Things are looking good, so the simulation is great. Let's run the subtract. To run the subtract simulation, we just need to change the target that we're shooting for, which is the sub, which is what I'm doing down here below, and just run the simulation. And there you have it. As before, we're going to look at the two inputs, A and B, and the output, and then the output flags. So we'll always be looking at the beginning, the positive edge of the clock. So here we have 0 minus 0, which leads to 0, and as expected, we have the 0 flag. On the next clock, we have 1 subtracted from 2, which leaves 1, as expected, and that is not a 0, nor overflows or anything else, so the flags are all correct. In this case, we're subtracting 1 from 0, which leads to a minus 1, and minus 1 is all F's. And in that case, we don't have a 0. We have a carry flag set, which in this case is called the borrow flag. It also yielded a negative number, or the most significant bit was set, and it also caused an overflow. On the next case, we're subtracting FF from FF on the lower side, and we get FF00. That's what we expect. We also expect that it's not 0, no carries or overflows, but it did set the negative flag because the uppermost bit is set. And the same thing from 1 subtracted from F gives FE, 2 from FF gives FD. That's as expected, no change in the flags. And then the last case is just an odd case where we take a small number and subtract a large number and we get another number. So there you go, that's the subtract simulation, and it's working great. Nice. The simulation looks good. Let's synthesize a top module onto the FPGA and see how it performs. As usual with synthesis, we're going to need a constraint file and a top file. So I will drag over my ALU, and here we have our constraint file, which has every single pin activated, and we need them all this time. And it also includes our top file. And as expected, we have a module that defines our top, lists all of our inputs and outputs, and then we have a bunch of local parameters that set up our frequency, the data width, which in this case we're going to do a 4-bit ALU. This makes it easier to see the LEDs on the display and provides us with a couple of extra pins that we can use to display some of the control signals. We got a bunch of defines for aliases, some registers for driving the devices under test. And again, we have a clock for the display of the green thing, just to let us know that everything went well. Got some useless initialize statements, but I put them there anyways. And now we start to get into the core of our synthesis. In this case, I have 3 behavioral blocks. One is looking at the ALU operation flag coming from our microcontroller. And the other is looking at the positive edge of source 1 so that we can track and move through the different types of data that we're going to add or subtract. And we're also watching the source 2. All 3 of these flags come from the microcontroller. Next up is our device under test, in this case the arithmetic logic unit, our source inputs, our function, the outputs, and our flag outputs. And then I've created 2 registers to capture our data from the ALU. We're going to capture the flags and we're going to capture the output. And then last, we drive all of the data out to the pins, which I will now show over here. This is the pins. To the right, we have, if you'll see the blinking LED here, we have the least 4 bits is the results. Then we have the ALU load state. Then we have the add subtract indicator. Then we have the source 2. And we have our 4 flags from the ALU and then source 1. We'll see that 2 bits will give us 4 different source values. And if we come back to our module, you can see that we have 4 different source values here. That's these. So we have all of our pin outputs right here. These are all of our outputs. And now we're ready to go. So the very first thing we want to do is set up and build our top module. So we'll come down here. We'll switch into the simulation or synthesis folder, like that. Tiny. And we'll switch into the ALU. And now we will do a make build. And there you go. It's created a make and a build. And here is the outputs from those commands. The next thing we want to do is do a route. And there we have it. It's been routed. So the next thing I'm going to do, now before I get this loaded up, I just want to reiterate that these flags over here, these 4 here represent the output of the ALU. This one represents the load state. These represent the counters. And then these 4 flags are the ALU flag results. And then this is source 1's, which pattern we're on here. So we have this pattern for source 2 and source 1. So now I'm going to come over here and push down on the FPGA load button. I'm going to come up here and do a make all. Make all, like that. And you can see now that it's uploading our stuff to the bit stream. So there you go. We now have our ALU on the FPGA. So the next thing is let's set up the microcontroller and understand how it works, and then we'll start testing our ALU. Okay, I've switched over to the microcontroller program, and don't worry, you really don't need to know anything about this. You can use whatever you wish to generate signals into your FPGA. I just happen to be comfortable with the expressive toolchain, so this is what I use. We have our usual 2 pins for clock and reset. We also have a source 1 and a source 2 pin to clock. We have a load pin to clock and an operation pin to clock. The way it works is that you can change between the add and the subtract by just selecting A or B, and you can pulse the source 1 clock or the source 2 clock and change the loading of the register manually, toggling it back and forth. That's all the microcontroller does. So let's start up the microcontroller. We've got it already loaded in. All we need to do is come down to the terminal here and start up the controller. So we will do a, let's see, there it is, monitor. I know that my device is connected to USB 0. So let's start it up and watch the lights over here on the FPGA when I start the monitor up. You'll see how they came up in unusual states. So I'm going to hit the S key to cycle the SR1 pattern, and that's this pattern over here on the left side. So we should see these two blue pins, which corresponds to this. I've tried to line it up with it. So if you kind of go at a diagonal, you'll see that they count. It's actually these two blue pins right here. So let me pulse the S clock, and you can see how it's counting, and now it's at its maximum, and then it'll go all to zeros. And I'm going to also do that for source 2. So you'll see it count up and then go to 0. And then if I hit the A and B key, you will see the ALU subtract flag turn on and off. So it's A now, and now it's gone to B. So it's on for B is subtract, and it's low. That's this little lead right here. We'll see, I'll do it again. It's on, and now it's off, so we're back to add. So now we're ready to actually test out the ALU. We're going to stay in the add mode. And we've got both of our sources. So let me come back to the source code up here, and we'll switch back over to Verilog project here and scroll down, and here's source 1 and here's source 2. That's what those pins do. So I've got them both set to 0. So it's going to try to add this one and this data here, which is 0 and 0. So 0 plus 0 should leave us with the Z flag. This green light should turn on. So let's give that a shot. So we will set the clock. We need to set the load clock to low. There we go. Now we'll run the clock. And as you can see, the Z flag, it went high. So far so good. We were able to add 0 plus 0, and that resulted in the Z flag going high. So now let's switch over to the source 2 to the number 1. So come over here and click the source flag. That's the D. And so now our pattern here on source 2 is 0, 1. So that corresponds to this flag right here. And now we'll pulse the clock once and see what happens. And as it's expected, the results went to the number 1, these last 4 bits. Also, the Z flag went off because the result is not 0, just as we expect. So let's pulse S2 and switch to the next pattern. So come over here, we'll pulse S2, and now we're at the next pattern here, 1, 0, and we'll clock 1. And as you can see, the carry flag went high, and that is because we actually added 0 plus 1, 0, 0, 0, and that caused the carry flag to go high, which is as we expect. So let's switch over to our last source that we have, pulse S2 again, and now they're both high right here, and we will run the clock one more time, and that's as expected. So now we're going to switch source 1. So we'll switch source 1 back to the next one. So now it's 0, 1 over here. And we're going to switch source 2 back to 0. So now it's all 0. And now we'll flip the clock. And as expected, 0, 1, or 1 plus 0 is 1. And we don't expect any of the flags to be on. So if we now move source 2 to the next value here and clock it, we should see this 4 bits right here switch to the number 2, which means this second bit will go on. So if we hit our clock, sure enough, it went on. Nice. Now we'll switch to this flag right here, source 2. We'll switch that one up. So we'll pulse that clock one more time, click add, and as expected, the negative flag went high. Alright, so now we're ready to try out the last one of the source 2. So we clock that, move the source there, and clock, and sure enough, we get the sum of the two, 1, 1, 0, 1. That's exactly as we expect. So we're doing okay. Looks like the adder is doing great. So let's switch over to the subtract and test out a few of those things. So to start the subtract, I'm going to hit the B key. There we go. Now I'm ready to switch all my sources back to the 0 state. So we'll count them up. There's that one to 0. We'll count that one went to 0. Go back around to 0. And now we are ready to, and I've reset the register. So let me pulse the clock. And there you go. The green light has gone high. And that's what we expect. The results 0 minus 0 is 0, which means it's the 0 flag goes high. So I'll switch the D pattern, and there you go, it switched. And now we're on D. So we're now subtracting 1 from 0, because source 1 is still setting at the pattern 0, and this one is now at 001. And as you can see, the 4 bits, just as we expected, all went high, because this represents -1 in 4 bits. And also, our 0 flag went low, but our carry went high, our negative went high, and the overflow. This is exactly what we saw in the simulation. So this is great. So let's switch source 2 to the next pattern right here. So I'll pulse the D key again, and I'll pulse the clock, and voila, we now have 1 -1001. And that wraps it all the way around back on itself and sets the highest bit. And as expected, we got a carry, and the negative flag is also high because of the last bit being high. And finally, we'll do one more pattern here, which I'll pulse it there. So now source 2 is maximum pattern. We'll clock it 1. And as expected, when we subtracted 1100 from this pattern up here, we get this value right here, which happens to only set the carry flag. And that's exactly what we expect. So it looks like the subtract circuit's working fine. I could go through the other patterns in here. We could take, for example, load up this pattern right here. So we'll switch source 1 to the third pattern. So I'll move it to the third pattern. There we go. 1, all right, 1, that's 1, and there's 2. So that's the third pattern. And run the clock. There we go. So we just subtracted this value here, we subtracted 1 from it, which as expected gave us 0, 1, 1, 1. And none of the flags are set. This is perfect. So I would say that the subtraction is working just from visual inspection. We now have a fully functional ALU, ready for integration into our processor. This gives us 2 major components, the register and the ALU. We are now ready to simulate and synthesize the next major component, the memory. This is where we will see for the very first time the initialize block honored by the toolchain. So until next time,